Good afternoon. My name is Ken Gingerich. I am not Owen. We switched places, so yeah, sorry about that. I am a first-year PhD student studying under Dr. Wayne Strasser. I'm continuing this research that Ryan Learn did. I'm the title of my presentation is Can Fluent Sufficiently Resolve Turbulence via Direct Numerical Simulation in a Wavy Channel? Before we try to answer that question, I need to kind of give you some background first. So we're kind of studying boundary layer control applications, or boundary layer control, and some of the applications are both hydrodynamic and aerodynamic. Airplanes, race cars, uh, subs, ships. We're like, for example, we're just looking at an airfoil on aircraft. As the airfoil increases its angle of attack, flow is going to separate, stall. Zooming in on that, the red is velocity profile. Yeah, velocity profiles. When the flow starts separating, the flow is reversing. And in that region of flow reversal, that's our uh, separation bubble. And so if we can kind of prevent that flow reversal, hopefully we can prevent the boundary layer separation, right? So this has a dramatic effect on lift coefficient. It's called stall, obviously. Uh, Not only on an aircraft, this also will increase pressure drag on race cars and everything like that. So what can we do to control the boundary layer? Well, we're looking into shark skin because it exhibits passive boundary layer control. If you look closely at shark skin, it's made up of minute scales called dermal denticles. They're on the order of 100 microns. This is an SEM image of one. Looking at them from the side, they can be bristled up into the flow, and that bristling action inhibits that flow reversal, thus preventing boundary layer separation. This is the bristling angle that I'll be talking about on this next slide. This is work done by Santos et al. In 2021. The legend or the colors are the fraction of time the flow is reversed. So right at 50%, that's when we would define flow separation. This is at a Reynolds number of 4.9 E5. Uh, this is on a flat plate. This is for shark skin with a bristling angle of 30 degrees, and that's shark skin with a bristling angle of 50 degrees. So at 50 degrees, shark skin is dramatically reducing flow separation. Yeah, and this also occurs at 7.1 and Reynolds number of 8.1. So you might be thinking sharks are cool, but I thought this presentation was about turbulent flow in a wavy channel. I will be getting to that, but this is just telling you what we're going to be using this for. So this previous work was examining the large scale characteristics. It lacks fine grained detail. We want to use direct numerical simulation to study shark skin. My advisor calls this downright Navier-Stokes. Uh, it's useful at low length scales, like on a 100 micron shark scale. It resolves turbulent flow, can visualize flow in the boundary layer, gives us broader quantity of data, but it's very computationally expensive, duh. In order to get to a DNS flow model of turbulent flow, first we need to validate our DNS methods. Then we need to implement our 3D moving frame mesh. Then we need to do our two-way coupled fluid structure interaction, and then we need to model and mesh our real dental geometry. This is our validation of our DNS methods. So just giving you a broader context of why we're doing this. So why are we doing a wavy channel? Well, this is streamlines from Unit All's paper in 2009. You can see the flow is separating and reattaching. This is span-wise averaged and time averaged. So the flow is constantly separating and reattaching over the wavy wall, and we need to validate our DNS methods specifically for this separation and reattachment to model for the shark skin. The second reason we want to use wavy wall is because it's canonical. There's a lot of data out there we can validate against, and we decided to do it against Unit All, their paper in 2009. So let's look at our model setup. This is our boundary, our model. Those are the geometry. Lambda is going to be our wavelength, 10 centimeters. Alpha is our amplitude of 0.5 centimeters. flow is moving in the positive x direction, y is our wall normal direction, and z is our spanwise direction. These are our faces of the boundary. To kind of explode that out, you can see that these are our periodic faces, and these are no-slip walls. This is just like a cosine wave at the bottom. We implemented a driving pressure gradient that was adjusted every time step to maintain constant flow rate. And the fluid is just air with air's properties. And we ran at a Reynolds number of around 6,600 with a bulk velocity of 0.896, and h is our mean channel height. So looking at our mesh statistics, in the streamwise direction, we have 250 cells. Spanwise, we have 100 cells, and wall normal, we have 150 cells for a total of 3.75 million cells. All structured hexahedral elements, and they have high orthogonal quality and low skewness. Looking closer, right down close to the wall here, there's like 68 uniform, like no bias in the cells right next to the wavy wall. We did this because we were trying to match unit all's mesh. Looking at their mesh, they had 82 cells that were on a hyperbolic tangent bias and 68 cells with no bias. So, and because they were using the immersed boundary method, because they were changing the amplitude of the wavy wall. Yeah. But we're not doing immersed boundary method, we're doing conformal mesh. So we're matching their bias right along the trench of the wavy wall. And then this is just kind of squished. So in order to match their hyperbolic tangent, we had to split it up into a bunch of bodies, because in ANSYS meshing, we can't use a function to define the grid distribution. It's just linear biases. So we split it up into a bunch to match their hyperbolic tangent function. So basically, this plot just says that we're matching their distribution. This is the uniform section, and then it's a hyperbolic up here. And we have an average error of less than 0.006%. So it's basically the exact same distribution in the trough, but it's a little squished here. We just doing downright Navier-Stokes. So momentum, continuity, incompressible viscous flow. Pressure velocity coupling is simple. We use least squared cell based. Second order pressure, second order momentum, first order transient. Then we just set the Courant number equal to 1. So these are preliminary results. This model has been running on a just potato of a computer for like a long time. And we finally put it on a cluster like a month back. But these are not fully time averaged. So yeah, some of the profiles are not fully time averaged. Most of them are though. So these are the streamlines. The top is Yoon's results. The color is just the magnitude of the velocity. And these are all spanwise and time averaged. So the shape is very similar to Yoon, but if you like kind of compare like the eye, I don't know if you can see the black kind of in the purple there, but it's kind of behind the dotted red line here. So we're kind of predicting the eye of that vortex to be a little bit farther back than Yoon does. This is a streamwise velocity. They didn't normalize by bulk velocity, so don't really pay attention to the numbers. Those aren't going to be the same, but the shape of the contours is very similar. But again, we are slightly back farther than they are at the kind of the eye, that negative flow region. This is the wall normal velocity. Again, don't pay attention to the numbers. It's not normal. It's not been normalized. And again, shapes very similar, but again, we're predicting it to be back farther. The turbulent kinetic energy profiles, these have been normalized the same way, so the numbers do mean something. They are showing more TKE right here than we are, 0.09. But other than that, the profiles are pretty same shape. Reynolds shear stress contours. Again, this is slightly higher than up here, but the shape is pretty much the same. And again, it's back farther in our study than on theirs. So now we're going to be looking at some profiles comparing. So this is the domain, looking at it from the XY perspective, and these are the 4 lines that we're going to be plotting over. x divided by lambda of 0.1, 0.3, 0.5, and 0.7. Remember, lambda is the wavelength. These are our mean x velocity profiles. Match pretty well. Worst place is right there on the 0.5, at the location 0.5 x over lambda. But it gets worse from there. These are TKE profiles. We're under predicting everything, but the shapes are very similar. Now we have our y velocity profiles. We're matching at 0.1 and 0.5 fairly closely, but kind of meandering off in 0.3 and 0.7. But these are the profiles that are taking the longest to collect enough data for. So those might not be fully time averaged enough. So I wouldn't take this with a grain of salt. And then we also plotted along the wavy wall mean pressure and mean shear stress. Very close on the pressure. Shear stress, we're deviating a little bit at the peak in the valley there. If you kind of extend the zero line, as they're crossing, that's where you would see the flow start to reversing. So right in here is like a separation bubble. So there's like a separation point. There's a reattachment point. There's another reattachment point. There's a separation point. So we're predicting the location of the separation point fairly well, but the reattachment point is, again, slightly off. So in summary, I kind of gave you background. This is we're trying to solve boundary layer separation, or at least reduce it, because that increases drag and reduces maneuverability. Talked about how shark skin could help to passively control these boundary layers. And then I explained why we're doing the wavy wall channel in order to validate our DNS methods for separating and reattaching flow. And we're validating against Unidol's study. So in conclusion, these are in fairly good agreement, I guess. They still need to be time averaged a little bit more, but yeah, the X velocity profiles are good. The TKE profiles are the most deviation. The Y velocity profiles match for a couple of them, but not for others. Pressure matches well, while shear stress deviates slightly. The separation point, we can predict that. We're predicting the same as Yoon did, but the reattachment is slightly off. So in the future, we just need to keep running this to make sure we're actually time averaging it. And then we might make some tweaks to our solution model, see if we can get a better fit. And then we need to continue making our DNS model of shark skin. If you remember this plot, we need to keep doing this and this. This we're done with. That's what Owen presented on. But these two we still need to do. Are there any questions? That's the reference of you if you want it.
So you're talking about doing the validation, but then you describe the Yoon paper as being the first boundary layer method, which implies to me that Yoon merely provided simulation results, which is not what I would consider a validation. Validation would be a data set comparison versus a model comparison, whereas it looks to me like you have a model versus model comparison. And so are you even appropriate saying we're invalid because we're not comparing correctly, or what gives them the accuracy, or were they bolstered by data? Can you further articulate that?
Yeah, they compared against experimental in their paper. All those plots, they matched the experimental very well. The reason we did this one is because they just gave a lot instead of the experimental study. We did this one because they gave us a lot more data that we could compare against. So yeah, maybe we should reference the original experimental study. Probably right about that. This is just a conference presentation. And if we would ever make a paper of this, we probably would do that. But thank you.
Why do you think your results are not matching? Because they're both DNS, right?
Yes.
Why?
Well, it's not fully time averaged. First of all, that could be resulting in some, but also this is the way they describe their bulk velocity is slightly different than what we did. So we might need to tweak that a little bit and keep running it. Yeah, so that's probably the reason we're running at a slightly different Reynolds number. Obviously, that needs to be changed, but that was just a mistake we did early on in the process, and that wasn't discovered till now. But yeah, that's probably the reason. But
Did you do a grid conversion study?
no, we're just trying to match their grid.
Why? Because your grid needs to first converge to reach its level of stable solution.
Okay.
What is the water level boundary condition?
Sorry.
Boundary condition, the water level.
Water level? There's no water level. It's
Yeah, you got a plot on that. Show your boundary conditions.
this boundary conditions. There's no water level. Oh, it's just a no slip wall at the bottom and a no slip wall at the top. Sorry if I don't understand your question.
I don't know if this is the question, but the DNS mesh that you showed
Mm-hmm.
looked like they had a different boundary condition on the top. Not yours compared to the other mesh.
Yeah, I'm trying to get there. Yeah.
You clearly have a wall at the top of your boundary.
Yep.
Height is small space. But when you, it doesn't look like they had a wall boundary condition. They had a zero gradient.
They did have a wall. I don't know if that image is accurate or not, but they definitely had a wall. At least, yeah, they said that in the paper. Definitely.
But you actually have two frogs in your domain area. Which one were we looking at roughly?
The
It doesn't matter.
it shouldn't matter. That the first one, we were looking at the first one. That's what, yeah. Yeah, all of these profiles and stuff, that's looking at the first one. The these ones are both.
Any further questions? All right, thank you.